we have Ken Goldberg. Ken is at UC Berkeley, and Ken really, I guess, he's everywhere. He needs no introduction. Fun fact: we're streaming this event, I think, to a satellite site in Africa, and Ken was born in Africa. Although I'd like to see your long-form birth certificate. Ken is a big believer in minimalist robotics. He's been working in manipulation for a long time, but lately he's been working on DEX, net, and foundation models. So I'd like to see how you kind of explain yourself. So please welcome Ken.
Thank you. Thank you, Frank. Okay, so this is really addressed to the younger generation here, and I'm going to start though by just going back 2 quick comments. One is that robots and art have a long history. As we know, the word actually came out of an art project and a theatrical performance. So I've been interested in this connection between art and robots for many years. This was something we did a long time ago called the Telegarden, where we let people control a robot from the internet. This was back in 1995. And recently I met Katie Kwan, who just finished her PhD at Stanford, and we started working together using OpenPose. And this was, we were just interested in capturing her motions. She's also a professional ballet dancer as well as a PhD in robotics. And so we were playing with these things, and then we decided to do a performance together around the issue of robots and work and all the fears out there that robots would take over and replace all the human workers. And also there's this beautiful history about time and motion studies and analysis of workers over the years. There's stop motion photography, etc. Even Marcel Duchamp used this idea in the context of his new Descending a Staircase. So we got the opportunity to give a performance in Brooklyn last year, and we called it Breathless. And it was an 8-hour modern dance performance at this place in Brooklyn, and I'll just show you a little clip of it. And you can see that she's playing with the motif of work. So there's a lot more there. I won't go into a lot of, we could talk more about that later. I also wanted to mention in terms of the ancient history here, my advisor, Matt Mason, is sitting right down in front, and this is a project that I did as a PhD student, which was to try and feed or orient objects, parts, with a parallel jaw gripper. And the highlight for me, at least, was being able to prove that we could do this for any polygonal object. And the proof was in my dissertation, and then we later, another student, when I was at USC, we were able to prove that we could extend this also to algebraic parts. All right, well, and then I found this photograph where I see some of the people who are still around are here. This is from only 30 years ago, another meeting after one of the ICRA conferences. So, is data all you need? And you've seen all this excitement. This has been the summer of humanoids. We've talked about them already. And you've seen these videos, Songbei mentioned. It's very exciting. There's huge amounts of money going into these fields. And part of what's driving this is this big advance in generative AI. And one of the ideas is, a big part of the idea is this end-to-end learning, that we could just take demonstrations of motions and actions and videos and then learn a model that would be able to replicate those in different environments. Now, there's some very interesting models out there that show that there is a potential for scaling for large models, that they seem to get better as the size of the model increases, and then size also requires more data. So people, like venture capitalists, actually one venture capitalist said this to me, well, large data has solved vision based on internet scale data, and then large data has solved language based again on internet scale data, and so therefore, large data will solve robotics. And I just want to raise a little question mark about this. And first of all, let's look at the dimensionality of these things. I mean, vision came first, actually, but it's a two-dimensional concept. And then we have language, which is really one-dimensional sequence of tokens. But robotics is really different. I mean, if you talk about humanoids, you're talking like 60-dimensional environments. And then also we have, in these other two cases, we have massive training data that's available from the internet in terms of images and language, but we don't have any for robotics. So I want to question this assumption that data is all you need. And let's just look at the case of self-driving cars. We have the case of, if you compare Tesla versus Waymo, and the amount of data it's estimated they have, Tesla has instrumented all of its cars so they get data from every driver. So they have a lot more, and a ratio of about 500 to 1 in terms of data. And yet, in terms of performance, Waymo is way ahead. And so this raises this question of, is data all you need? And when you look at Waymo and look a little more closely at what's going on there, it's a lot of data, but also what I call good old-fashioned engineering. And that is, there's a lot of sensors, there's a lot of submodules. Basically, it's good old-fashioned engineering is modularity and algorithms and metrics. And I want to contrast that with generative AI, which is really this end-to-end idea. And for example, OpenX, we all know about it. It was very celebrated at ICRA this year. Lots of robots, a fair amount of data, some terabytes of data. But there's some concerns I have. For example, the success rates are not that good. We're talking about, well, at best, 60 to 80%. And success isn't even well defined in these cases. It's usually self-reported and subjective. Like, what does it mean for a success when you line up 8 blocks, right? It's really just binary classification of that as success or failure is a little problematic to me. And also all the tasks. You know, there was a claim that one of the projects had 160,000 tasks represented. But when you actually did a little analysis on it, and this is a linguistic analysis, you actually see that almost all the tasks are basically pick object 0 and place it in object 1. So that actually turns out to be very well understood. And if you go to the fundamental textbook from Russ Tedrake, he's got a whole chapter on pick and place. It doesn't mention anything about deep networks. And basically what it's all about is good old-fashioned engineering, modularity, algorithms, and metrics. Now, I also want to say this has been captured in the wonderful book. Osama and Bruno have put together this wonderful series, this 2,000-page tome, the Handbook of Robotics. And I don't think that we should just dismiss this thing. In fact, the way I like to put it, here's large models. You may have remembered during the Olympics, and here's good old-fashioned engineering. So I just really quickly, in computer vision, there was this big success with ImageNet. We try to do the similar thing with data, for grasping, in particular for what we call DexNet, dexterity network. Basically collect a very large data set of grasps. And we were able to do that, and I won't go into details about how we did it, but basically we could generate very quickly using simulation and analysis and perturbation analysis some millions of examples of good and bad grasps with noise injected into those. And then we had this performance where the system was able to routinely clear bins with objects that it had never seen before. So it was able to generalize. It was fairly robust. The success rates were on the range of 90 plus, not 100%, but we also had fairly high pick rates and consistently was able, but this is using a parallel jaw gripper and a suction cup to clear this bin. So this was in Science Robotics, and I want to tell you a quick story about how we got the chance to demonstrate this to Jeff Bezos, and his assistant put his shoe into the things. Well, will it work with the shoe? Now, my mouth went dry because we've never tried it with a shoe before. And here's the system lifting the shoe out. I called my wife and I said, this was the best moment of my life. Anyway, we came home that night and the students decided to form a company. And so we formed Ambi Robotics. We're now in our 5th year. This is a product we make. It's Ambi Sort. It's a system that picks objects out of bins using that technology and then scans them and then sorts them into smaller bins according to zip code. So this is basically to address the surge of e-commerce. So we're now sorting 1 million packages a week. We have 60 of these machines all over the United States. What's also kind of cool is that we get data from all these machines. So we actually have a flow of data. Every single machine, every instance, every pick is recorded and sent back to us. So we can keep track of what's going on all the machines, but we also can do A/B testing with different modifications to the algorithm over time. Now, I mentioned here because it's data, so maybe you might say, is data all you need? And I would say no. It was really data plus good old-fashioned engineering. So what's a huge part of this project is modularity. There's a lot of modules that go into making each of these systems. There's algorithms, in particular motion planning algorithms, and a number of innovations that had to be made there to make those fast and efficient. And then metrics, and a whole bunch of metrics that I didn't really think about as an academic that turned out to be very important in industry. Now, so I'm advocating for this combination of data and large models with good old-fashioned engineering. And my students and I put together this paper, which will come out in IROS next month, which is an architecture for doing this that we call MANIP, Modular Architecture for Integrating Good Old-Fashioned Engineering with Learned Models. And this is joint with some colleagues at Toyota, TRI. And I'll just give you an example of this. Here's a problem, a manipulation problem called bagging. And that's something you and I do, we all do every day. We just want to take a bag, open it up, and put some objects into it. Well, it's really easy for us, but it's extremely difficult for robots, according to, again, classic example of Moravec's law. And because you can't perceive these bags. So what we did was we had a deep learning system train itself to be able to do this by using ultraviolet paint, painting the bags, and then using ultraviolet cameras to get labeled images. Basically, the system can self-generate these labeled images, and then it can learn from those to be able to identify the bag features and then be able to perform this task. Now, if you look at the success rate, it's not very good. We're talking about like 50%. So it's still failing a lot. Now, this is where we applied MANIP, this new architecture. And what we did was we added a new module. And that is in green here. It's an interactive perception module that basically we call it SLIP. And what it is the key part of the failure mode of this system was that we couldn't singulate individual layers of the bag. That was the problem. So we wanted to be able to do this. So this is what you just illustrated there, was that we had to iterate very carefully to actively determine if we have one layer of the bag. That was just this module, very, very much of a good old-fashioned engineering module that we put in the middle of this. And so then we were able to, the performance went up quite a bit. We were able to manipulate these bags much more reliably. We could also extend it to different kinds of bags, so it started to generalize. And so our performance beforehand, and you can see here, is fairly low, actually 0 for these to generalize to these other bags. But after we added this good old-fashioned engineering module, then performance went up dramatically across the board. That's the columns, the numbers you see in green. So I want to say that we can talk more about this later and during conversations and over the next couple days. I am a little concerned about all this excitement, this irrational and exuberance, and I'm worried about another AI winter. Again, the younger generation doesn't know what I'm talking about, but there have been these winters over time. I think we're at this stage right now where there's a lot of expectations, and we have to be careful about a trough of disillusionment. And I'm worried about not only a winter, but maybe even a blizzard of negative feedback, basically of disillusionment that may occur if we're not able to deliver. So I'm not trying to basically rain on the parade and say that this is not a good thing, but I just think it's important to maybe not stop the enthusiasm, but curb the enthusiasm around what we're going to be able to do with deep models. And I was reminded of this idea we just were talking about a couple years ago. We can't stop the pandemic, but let's flatten the curve. Just slow the expectations or slow the enthusiasm a little bit so that we can actually live up to the expectations. All right, so I want to thank my terrific students who I've been lucky to work with in over here and recently and over the years. Our sponsors that I've been, it's been such an honor to work with. And I want to say happy 40th birthday to ICRA and good old-fashioned engineering. Thank you.
Excellent. Nice job, man. Yeah, thanks very much, Ken. Let's see. I've been told we're going to have a break. Everything's been delayed half an hour, so we're going to have a half-an-hour coffee break, and this will allow those who have not registered to go ahead and complete your registration. Maybe one quick question for Ken before we break. Anybody?
Ken, thanks.
Yeah.
Great talk, of course. I mean, I note you highlight the fact that self-driving cars are taking billions of hours of data and still not able to drive a car. Compare that to a human that takes only 25 hours and can drive a car. You talk about good old-fashioned engineering as compared with end-to-end models. Isn't essentially what you're doing merely adding additional structure to a model with your good old-fashioned engineering approach? And isn't the problem that the way we're thinking about structuring end-to-end AI models perhaps not the right way?
Oh, okay, that's the question. Good. Yeah, I think you're onto something. I think that's right. There's, the existence proof is that deep learning obviously does work because we're humans, right? And we seem to work under some approximation of that. So I do think there's going to be breakthroughs in the structure of how we do this. And for example, I think that the transformer model was a breakthrough that was extraordinarily important. And there may be something like that coming. I think the key I'm trying to say is we haven't seen that yet. These problems are much more complex than most people assume. I think everybody in this room knows this already, right? But I think the public doesn't. And Sangbei was basically making the same argument that these problems are very deep and robotics is much more complex than language. So we're not there yet. We need those additional breakthroughs, and it'll be in the form of new structure, like transformer models. But we don't know when those are going to come. And right now, our friends, Musk and Jensen Huang are basically claiming we're now ready, and it's going to happen around in the next year or so. And that's what I worry about. So I think it's important for us to go out there and just sort of, not just push back on that a little bit. And for the younger generation out there, and thank you for being here, by the way, because you're here to celebrate this wonderful 40 years, that all this vast work is actually extremely valuable and actually will be part of, I believe, this structure that we're still waiting for. Thank you.